Imagine you're standing on a long stretch of railroad track. The steel rails stretch endlessly into the horizon, perfectly straight, perfectly aligned. Now, you probably know that when materials heat up, they expand. It's something we've all seen. Sidewalks cracking, bridges equipped with big metal joints, even your car making little popping sounds on a hot day. So here's the question. Steel expands a lot when it gets hot.
Curious about how the world really works? Not the myths, not the shortcuts, the real science behind everything we see and experience. On this channel, we explore mind-bending physics, unravel the secrets of the universe, and uncover the hidden patterns that shape our reality. If that excites you, subscribe for weekly deep dives into science and discovery. Hit like and share with friends. Your curiosity drives our next adventure. Leave a comment and let us know what puzzles we should solve together.
In fact, a 1 kilometer length of steel rail can grow by several centimeters during the heat of summer compared to the chill of winter. That's not a small shift. It's enough to cause buckling, bending, and even dangerous derailments if it's not controlled. That's why, when you look at bridges or concrete roads, you'll often see those very visible expansion joints. Little gaps or flexible connectors that let the material grow and shrink without destroying itself. But here's the puzzle. Railroads don't seem to have them. When you walk along a modern railway, you don't see big gaps between the rails. You don't see joints every few meters designed to absorb that thermal expansion. Instead, the rails are continuous, running smoothly for kilometers on end. So how on earth do railroads get away with this? Why don't they need expansion joints when pretty much every other massive metal or concrete structure does? Well, the answer is both a story of old versus new engineering and a fascinating dive into physics, material science, and clever human innovation. And once you see how it all comes together, you'll never look at train tracks the same way again. Before we dive in, let's go back in time, because the way railroads used to be built is very different from what you see today. Back in the 19th and early 20th century, railways absolutely did use expansion joints. They had to. Rails were short, usually only 12 to 20 meters long, and they were bolted together with what were called fish plates. Between these segments, there were gaps deliberately left so that the rails could expand and contract without pushing against each other. If you've ever ridden an older train and heard that rhythmic clickety-clack sound under the wheels, that was the sound of the wheels passing over those joints. Every few meters, another gap, another sound. At the time, nobody thought much of it. That was just how railroads sounded. In fact, that sound became almost synonymous with train travel itself. But those joints weren't perfect. They created weak points in the track, where bolts could loosen, rails could crack, and maintenance crews had to constantly inspect and repair. Not to mention, the ride wasn't as smooth as it could be. As trains became faster and heavier, those joints became a liability. The constant pounding from train wheels wore them down quickly. They also made it harder to maintain precise alignment of the rails, which is crucial for safety. Engineers started looking for a better solution, and eventually they found one. Instead of dealing with thousands of small expansion joints, why not make the rails themselves continuous, stretching for hundreds or even thousands of meters? That's where the idea of Continuous Welded Rail, or CWR, came in, and it changed everything. But here's the twist. Welding rails together doesn't magically make steel stop expanding. It still wants to expand in summer and contract in winter. The difference is in how that expansion is controlled and where the stress actually goes. And to understand how this works, we need to look at the physics of steel, the way railroads anchor their tracks, and the remarkable techniques engineers developed to manage forces that can reach hundreds of tons. How continuous welded rail works, and why expansion joints became obsolete. To understand why railroads don't need expansion joints anymore, we need to first get inside the mind of a railway engineer. Imagine you're tasked with laying down a steel rail that will endure blazing summers, freezing winters, and the pounding weight of locomotives that weigh hundreds of tons. Your first thought might be, steel expands and contracts. We need gaps. That's what older engineers believed, and that's exactly what they built. But those joints had problems. Constant maintenance, noise, misalignments, and even accidents. So the question became, what if we could make steel behave differently? Enter Continuous Welded Rail, or CWR. Instead of laying tracks in small segments and bolting them together, engineers now weld long sections of rail into one continuous piece. These welded lengths can stretch for kilometers without a single joint interrupting them. The result is smoother rides, fewer weak spots, and less wear on trains and tracks alike. But again, that nagging question, what about expansion? Here's the genius part. Engineers discovered that by anchoring the rails to the sleepers, or railroad ties, and the ballast, the crushed stone bed under the track, they could restrain the natural expansion and contraction of steel. Think about it this way. If you take a thin metal rod and heat it, it can expand freely. You'll see it grow longer. But if you clamp it tightly on both ends with massive force, it doesn't expand outward as much. Instead, it builds up internal stress. And steel, being incredibly strong, can hold that stress without breaking, as long as it's carefully managed. That's exactly what happens with modern railways. When CWR is laid down, it's not just welded and forgotten. Engineers use a concept called the neutral temperature. This is the temperature at which the rail is installed and locked into the track bed. Typically, it's chosen to be somewhere around the average between the hottest and coldest expected temperatures in that region. For example, if a place ranges from -10 degrees C in winter to 40 degrees C in summer, the neutral temperature might be around 25 degrees C. That means at 25 degrees C, the rail is stress-free. At hotter temperatures, the steel wants to expand, but the clamps and ballast hold it in place, creating compressive stress inside the rail. At colder temperatures, it wants to contract, but again, it's held in place, creating tensile stress instead. So the rail isn't expanding and contracting freely like a bridge joint or a sidewalk slab. It's being forced to hold all that expansion energy internally. Now, you might be thinking, doesn't that eventually cause failure? After all, steel can only take so much stress. And you'd be right if the design weren't clever enough. Railroads are built with incredibly strong fastening systems. The ties are spaced precisely, the ballast is compacted tightly, and the rail itself is massive, often weighing over 60 kilograms per meter. This combination creates a track structure so rigid that it can resist the expansion forces of the rail. Instead of moving freely, the steel just stores that energy as internal stress. Of course, there are limits. If the rail gets much hotter than expected, it can buckle, a dangerous phenomenon called a sun kink. You've probably seen photos of tracks bent into wild curves like spaghetti under extreme heat. These are rare but serious incidents, and rail companies monitor rail temperature closely to prevent them. On the flip side, extreme cold can make rails brittle and increase the risk of fractures. That's why inspection crews, temperature monitoring systems, and strict maintenance schedules are all part of modern railway operation. But when managed correctly, continuous welded rail can last decades with far fewer problems than jointed track. And here's another benefit. Without expansion joints, trains can travel much more smoothly and quietly. That iconic clickety-clack sound of wheels hitting gaps? It's mostly gone. Modern train rides feel more like gliding than rattling, all thanks to the seamless nature of welded track. So, to answer the question, why don't railroads need expansion joints? It's because engineers figured out how to anchor the rails so firmly into place that instead of physically moving with temperature changes, the steel just holds the stress internally. Expansion joints became unnecessary, at least on straight sections of track. But there's still more to the story, because while most of the track network today is built using continuous welded rail, there are still specific locations where expansion joints are necessary. And understanding those exceptions gives us an even deeper appreciation of railway engineering, where expansion joints are still needed and the hidden risks of CWR. So far, it might sound like continuous welded rail is the perfect solution. No gaps, no clickety-clack, fewer maintenance headaches, smoother rides. But in engineering, nothing is ever that simple. The truth is, while most of the railway network today is built using continuous welded rail, there are still specific locations where expansion joints are necessary. And understanding those exceptions tells us a lot about the hidden risks of rail technology. Let's start with bridges. Bridges expand and contract independently of the tracks laid on top of them. Concrete or steel bridges can move quite a bit with temperature swings, and if you weld a continuous rail solidly across them, the movement of the bridge will tear the track apart. To solve this, engineers install special rail expansion joints at the ends of bridges. These joints don't look like the old-fashioned track gaps you might be picturing. They're often more sophisticated, with overlapping rails or sliding mechanisms that let the steel adjust length without leaving a dangerous gap. Another place you'll still see expansion joints is at switches and crossings. These are complex pieces of track that let trains change from one rail line to another. Because they already contain moving parts, the stresses from expansion can't be safely absorbed without some allowance for movement. So here too, specially designed joints come into play. But outside of those situations, the continuous welded rail is king, which brings us back to its hidden risks. Remember earlier when I mentioned sun kinks? This is the nightmare scenario for railway operators. Imagine a blazing summer day. The steel rail is already hundreds of meters long, is trying to expand even further. The ballast and ties are holding it down, but if the internal compressive stress gets too high, the rail can suddenly buckle sideways. And when a train hits a kinked track at full speed, the results can be catastrophic. That's why track maintenance teams pay so much attention to rail temperature. In many parts of the world, railways use infrared sensors, drones, or even special patrol trains to constantly monitor track conditions. If the rail temperature gets dangerously high, speed limits are imposed to reduce the risk of derailment. In extreme cases, trains might even be stopped entirely until the heat subsides. On the flip side, cold weather creates its own problems. As the rail contracts, it builds up tensile stress. And if there are microscopic flaws in the steel, tiny cracks invisible to the naked eye, those stresses can cause the rail to snap suddenly. A broken rail can derail a train just as easily as a sun kink. So while CWR has eliminated the need for most expansion joints, it hasn't eliminated the need for careful engineering and constant vigilance. Railroads also face another subtle challenge, the neutral temperature I mentioned earlier. When the track is installed, it's locked in at a specific temperature, usually chosen to be the average of the local climate. But what if the rail is installed incorrectly? If workers weld the track in place on a cooler day than intended, the neutral point shifts and the stresses across the year become much larger than expected. That means more risk of buckling in summer and more risk of breakage in winter. In fact, many derailments around the world can be traced back to poor installation practices, where the neutral temperature wasn't properly managed. It's a delicate balance. The rails must be anchored tightly enough to resist ordinary expansion forces, but not so tightly that they can't flex slightly when needed. That's why modern railways use precise tensioning equipment during installation. Workers heat or stretch the rail to exactly the right length before welding it, ensuring it's perfectly balanced for the climate where it's laid. So yes, railroads today don't need expansion joints along most of their track. But behind that simple truth is a system of constant monitoring, careful installation, and backup safety measures. Expansion hasn't disappeared, it's just been absorbed and managed in a smarter way. And this leads us to a bigger, almost philosophical point. Sometimes, the best engineering isn't about avoiding a problem entirely, but about learning how to live with it. Continuous welded rail doesn't stop steel from expanding. It just makes that expansion invisible, hidden within the stresses of the material.
The result is a track system that's smoother, safer, and longer lasting than anything from the early days of railroading. But it's also a system that demands respect, because the forces at play are immense. A single kilometer of rail in the summer sun can be pushing with hundreds of tons of force against its own anchors. Managing that kind of power requires not just clever design, but also trust in the materials, the workers, and the constant vigilance of railway operators. And it makes you appreciate the next time you glide along a train journey how much hidden engineering lies beneath your feet. History of expansion joints and the shift to CWR. If we rewind to the early days of railroads, the story looks very different. Back then, rails were made in short lengths, sometimes no more than a dozen meters. They were joined with bolts and fish plates, metal connectors that held the ends together. But because steel expands, workers left small gaps between each piece. These were the expansion joints of the past. And this design had a sound, the famous clickety-clack that train passengers used to associate with rail travel. Each time a wheel crossed a joint, it struck the gap. Nostalgic, yes, but also inefficient. Those joints were weak spots. They loosened under stress, caused wear on wheels, and made the ride rougher. Maintaining them was a constant battle for railway crews. The solution came gradually, as welding technology improved in the mid-20th century. Instead of building tracks out of countless short pieces, engineers began welding them into continuous welded rail, or CWR. By the 1950s and 60s, countries like the US, UK, and Germany had begun large-scale adoption. This shift was revolutionary. Suddenly, tracks were quieter, stronger, and longer lasting. Expansion joints, once everywhere, were now only needed in special cases like bridges or switches. It's almost poetic. The sound of the old railways fading away, replaced by the near silence of modern trains, gliding on continuous rails. What once was a constant engineering headache became an elegant solution hidden beneath our feet. And it's why today, when you walk along a track, you won't find the gaps you might expect. Expansion joints haven't vanished entirely, but for most of the railway, they've become a relic of history. So why don't modern railroads need expansion joints? It comes down to this. Instead of letting steel expand and contract freely, engineers learned to control that movement. By welding rails into continuous lengths and anchoring them firmly into sleepers and ballast, the expansion energy is absorbed as internal stress rather than outward motion. Expansion joints still exist, but only where they're absolutely necessary, like on bridges or switches. Everywhere else, the smooth, seamless track is a triumph of engineering. And it's not without risks. Sun kinks, code fractures, and installation mistakes can all lead to disaster if railways aren't monitored closely. But with modern technology, careful installation, and constant vigilance, those risks are managed. The result is the railway you see today. Faster, quieter, stronger, and safer than ever before. Next time you're on a train, notice the silence under your feet. No more rhythmic clatter of wheels hitting daps, just the steady hum of steel against steel. That silence is the sound of engineering progress. The reason railroads don't need expansion joints anymore.